GFCI receptacles are not available in the auto-ground style because the auto-ground mechanism relies on a metal yoke to provide the grounding path. GFCI receptacles require a separate grounding conductor connected to the grounding terminal or a wire lug attached to the receptacle box. Section 250.146 of the National Electrical Code requires that GFCI receptacles be installed with a ground fault circuit interrupter device that is listed in accordance with Underwriters Laboratories 943 or equivalent standards. Auto-grounding receptacles utilize a spring steel yoke that contacts the side of the receptacle box, providing a grounding path. However, GFCI receptacles are designed to be installed in both metal and non-metal boxes, and a reliable grounding path cannot be guaranteed in a non-metal box. Without a dedicated grounding conductor, the GFCI device would not be able to properly protect against ground faults. A broken yoke or loose connection in an auto-grounding mechanism could defeat the purpose of the GFCI. Section 250.146 of the National Electric Code applies to GFCI receptacles. This section covers the installation requirements for GFCI devices, including receptacles, and requires that they be installed in accordance with the manufacturer's instructions and the applicable standards. Let's delve deeper into why GFCI receptacles don't use auto-grounding and how the grounding requirements of the National Electric Code, specifically Section 250.146, play a role. First, it's essential to understand the function of a GFCI receptacle. It's designed to protect people from electrical shock by monitoring the current flowing in the circuit. If it detects an imbalance, meaning some current is leaking to ground, it quickly trips and cuts off the power. This imbalance, even a very small amount, can be dangerous to humans. The key to a GFCI's operation is having a reliable grounding path. This grounding path provides a low impedance route for fault current to flow back to the source, which is essential for the GFCI to detect the fault and trip. Auto-grounding receptacles rely on a spring steel yoke making contact with the receptacle box to create the grounding path. This works reasonably well when the box is metal and properly grounded. However, this method has some inherent limitations. Firstly, the connection between the yoke and the box can become loose or corroded over time, increasing the impedance of the grounding path and reducing its effectiveness. Secondly, auto-grounding is not reliable when the receptacle box is made of non-metallic material like plastic. In this case, there is no grounding path for the yoke to connect to. This is where the design of GFCI receptacles differs significantly. They are designed to be installed in both metal and non-metal boxes, and therefore they cannot rely on the auto-grounding mechanism for a reliable grounding path. Instead, GFCI receptacles require a direct connection to the grounding system through a dedicated grounding conductor, typically a green or bare copper wire. This grounding conductor must be connected to the grounding terminal in the receptacle and run back to the main grounding electrode system of the building. This ensures a low impedance grounding path regardless of whether the receptacle box is metal or non-metal. The National Electric Code, NEC, in Section 250.146 reinforces these requirements for grounding receptacles. It specifies the methods for grounding equipment, including receptacles, and emphasizes the importance of a continuous and effective grounding path. For GFCI receptacles, Section 250.146 mandates that they be installed according to the manufacturer's instructions and the applicable standards. This means that they must be connected to a properly installed grounding system, which includes a grounding electrode, a grounding conductor, and a grounding terminal. The reason the code is so strict about grounding is that a faulty grounding system can have serious consequences. If a ground fault occurs and there is no reliable grounding path, the fault current may flow through a person who comes into contact with the energized equipment, resulting in electric shock or even death. A properly installed GFCI receptacle with a dedicated grounding conductor provides a much higher level of protection against these hazards. It's also important to understand the role of Underwriters Laboratories, or UL, Standard 943. This standard specifies the requirements for GFCI devices, including receptacles. It includes tests for performance, safety, and reliability. GFCI receptacles that are listed under UL 943 have been tested and certified to meet these requirements, providing assurance that they will perform as intended. In summary, GFCI receptacles do not use the auto-grounding method because it is not reliable in all situations. They require a dedicated grounding conductor to ensure a low-impedance grounding path, regardless of the type of receptacle box. Section 250.146 of the National Electric Code reinforces these grounding requirements, and UL 943 provides a standard for GFCI device performance. By following these guidelines, it ensures the safe and effective operation of GFCI receptacles, protecting people from electrical shock hazards. Now, let's expand on some practical considerations related to GFCI installation and grounding. Firstly, when replacing a non-GFCI receptacle with a GFCI receptacle, it's crucial to verify the presence of a grounding conductor in the box. In older wiring systems, a grounding conductor may not be present. In such cases, it might be permissible to replace the non-grounding receptacle with a GFCI receptacle, but it must be labeled no equipment ground. While this provides a degree of shock protection, it's not a substitute for a properly grounded receptacle. Secondly, when installing GFCI receptacles in bathrooms, kitchens, and other wet locations, it is essential to use weatherproof covers. These covers protect the receptacle from moisture, which can cause corrosion and create a shock hazard. Thirdly, it's crucial to test GFCI receptacles regularly to ensure they are functioning correctly. Most GFCI receptacles have a test button that simulates a ground fault. When the test button is pressed, the receptacle should trip and cut off power. If the receptacle does not trip, it should be replaced immediately. Fourthly, when wiring GFCI receptacles, it's important to follow the manufacturer's instructions carefully. GFCI receptacles have specific terminals for the line and load wires, and wiring them incorrectly can prevent them from functioning properly. The line wires are the incoming power wires, and the load wires are the wires that continue on to other outlets or devices. Fifthly, when extending a circuit from a GFCI receptacle, it's important to protect the entire circuit with GFCI protection. This can be done by wiring the downstream receptacles to the load terminals of the GFCI receptacle. However, it's important to note that this can create a nuisance tripping situation if a ground fault occurs in the downstream circuit. Sixthly, when dealing with aluminum wiring, it's especially important to use receptacles that are rated for use with aluminum wiring. Aluminum wiring expands and contracts more than copper wiring, and this can cause loose connections and overheating. Seventhly, when installing GFCI breakers in the electrical panel, it's important to make sure that the breaker is compatible with the panel. Some panels require specific types of breakers. It's also important to label the GFCI breakers clearly so that they can be easily identified. Eighthly, when performing electrical work, it's always important to turn off the power at the breaker box before starting any work. This prevents accidental electric shock. It's also a good idea to use a voltage tester to verify that the power is off before touching any wires. Ninthly, when working with electricity, it's always important to wear appropriate safety gear, including safety glasses and rubber gloves. Safety glasses protect the eyes from flying debris, and rubber gloves protect the hands from electric shock. Tenthly, if you are not comfortable working with electricity, it's best to hire a qualified electrician. Electricians have the training and experience to perform electrical work safely and correctly. Furthermore, let's consider some specific scenarios where GFCI protection is required by the National Electric Code. 1. Bathrooms. All 125 volt, 15 amp and 20 amp receptacles installed in bathrooms must have GFCI protection. This is because bathrooms are wet locations and the risk of electric shock is higher. 2. Kitchens. All 125 volt, 15 amp and 20 amp receptacles serving countertop surfaces in kitchens must have GFCI protection. This is because kitchens are also wet locations, and there is a high risk of electric shock from appliances. 3. Outdoors. All 125 volt, 15 amp and 20 amp receptacles installed outdoors must have GFCI protection. This is because outdoor receptacles are exposed to the elements, and the risk of electric shock is higher. 4. Crawl spaces. All 125 volt, 15 amp and 20 amp receptacles installed in crawl spaces must have GFCI protection. This is because crawl spaces are often damp and difficult to access, and the risk of electric shock is higher. 5. Unfinished basements. All 125 volt, 15 amp and 20 amp receptacles installed in unfinished basements must have GFCI protection. This is because unfinished basements are often damp and have concrete floors, which increase the risk of electric shock. 6. Swimming pools. All receptacles within a certain distance of a swimming pool must have GFCI protection. This is because swimming pools are extremely wet locations, and the risk of electric shock is very high. 7. Boathouses. All receptacles in boathouses must have GFCI protection. This is because boathouses are located near water, and the risk of electric shock is higher. 8. Garages. All 125 volt, 15 amp and 20 amp receptacles in garages must have GFCI protection, with some exceptions for receptacles that are not readily accessible. 9. Laundry areas. All 125 volt, 15 amp and 20 amp receptacles in laundry areas must have GFCI protection. 10. Within 6 feet of sinks. All 125 volt, 15 amp and 20 amp receptacles within 6 feet of a sink must have GFCI protection. These are just some of the locations where GFCI protection is required by the National Electric Code. It's important to consult the code for specific requirements in your area. The National Electrical Code is a comprehensive set of standards for electrical wiring and equipment. It is updated every 3 years to reflect the latest advancements in technology and safety practices. It is important for electricians and homeowners to stay up to date on the latest code requirements to ensure the safety of electrical installations. Continuing on, it is also crucial to understand the difference between GFCI protection and arc fault circuit interrupter, or FSI protection. While both devices protect against electrical hazards, they do so in different ways. GFCI protection protects against ground faults, which occur when current leaks to ground. FSI protection protects against arc faults, which are dangerous electrical arcs that can cause fires. GFCI receptacles are typically installed in wet locations, such as bathrooms and kitchens, while FSI breakers are typically installed in the electrical panel to protect entire circuits. In many new homes, both GFCI and FSI protection are required. Another important consideration is the proper sizing of conductors and overcurrent protection. Conductors must be sized to carry the expected load, and overcurrent protection, such as circuit breakers or fuses, must be sized to protect the conductors from overload. Using undersized conductors can cause overheating and fires, while using oversized overcurrent protection can allow excessive current to flow, damaging equipment. The National Electrical Code provides detailed tables and guidelines for sizing conductors and overcurrent protection. Furthermore, it's important to understand the concept of voltage drop. Voltage drop occurs when the voltage at the end of a long circuit is lower than the voltage at the beginning. Excessive voltage drop can cause equipment to malfunction and can also lead to overheating. A National Electrical Code provides guidelines for limiting voltage drop to acceptable levels. It's also important to understand the different types of wiring methods that are permitted by the National Electrical Code. Common wiring methods include non-metallic sheet cable, or NM cable, which is commonly used in residential wiring, and metal conduit, which is commonly used in commercial and industrial wiring. Each wiring method has its own advantages and disadvantages, and the choice of wiring method depends on the specific application. It's also important to understand the proper methods for making electrical connections. Electrical connections must be made in a way that ensures a reliable and durable connection. Common methods for making electrical connections include wire connectors, such as wire nuts, and terminal screws. It's important to use the correct type of connector for the application and to tighten the connections properly. Moreover, it's important to understand the requirements for grounding and bonding. Grounding is the process of connecting electrical equipment to the earth, which provides a path for fault current to flow back to the source. Bonding is the process of connecting metal parts of electrical equipment together to create a continuous electrical path. Proper grounding and bonding are essential for preventing electric shock and fires. Additionally, it's essential to understand the requirements for electrical clearances. The electrical clearances are the minimum distances that must be maintained between electrical equipment and other objects. These clearances are designed to prevent accidental contact with energized equipment and to allow for proper ventilation. The National Electrical Code provides detailed guidelines for electrical clearances. Finally, it is paramount to always prioritize safety when working with electricity. Electricity is a powerful force that can be dangerous if not handled properly. By following the safety guidelines and best practices outlined in the National Electrical Code and other resources, one can minimize the risk of electrical hazards and ensure a safe electrical environment. It is advisable to consult with a qualified electrician for any electrical work that you are not comfortable performing yourself.